Hello everyone, and welcome to my presentation. Today, I am thrilled to present our research on frame complexity-aware foveated video encoding for real-time high-quality streaming. In this presentation, I will discuss a fundamental flaw in how current foveated video encoding be designed and implemented in cloud VR system to optimize the bandwidth usage. Specifically, we will explore how frame complexity affects the encoded frame size during manually quality assignment of foveated video encoding. And more importantly, we will share how we solve this by introducing a real-time, complexity-aware framework powered by GPU compute shaders. Let us start with a brief background. Cloud VR delivers highly immersive experiences to lightweight headsets. However, streaming high-resolution, high-frame-rate video demands substantial network bandwidth. To mitigate this, foveated video encoding, or FVE, are widely explored. By assigning lower quantization parameters, or QP, to the foveal region and higher QP to the periphery, FVE significantly reduces bandwidth demands while preserving perceptual quality. To achieve ultra-low latency, this process relies heavily on standard hardware encoders like NVIDIA's NVENC. But here lies a fundamental challenge: the conflict between rate control and foveation. There are three primary rate control modes for hardware encoders. While the other two modes CBR and VBR estimate frame complexity for rate control, they do not support manual, per macroblock QP adjustments required for foveation. Therefore, FVE is implemented with constant rate factor mode, which disables the rate control and solely relies on QP. However, standard hardware encoders manage bitrate through an internal, black box rate control mechanism. They estimate scene complexity and calculate a base QP before foveation even happens. Because FVE forces manual QP adjustments after the built-in rate control has already run, it bypasses the control loop. This means the encoder is completely blind to the actual foveated frame size. If a player enters a highly complex scene with rapid motion, the encoding will blindly overshoot the target bitrate, causing massive network congestion and latency spikes. Conversely, in simple scenes, it will undershoot, wasting available bandwidth and degrading visual quality. To solve this, we must measure frame complexity. But we discovered a critical issue. As shown in the figure, when using standard uniform encoding, standard ITU complexity metrics correlate strongly with the encoded frame size. However, under FVE, the correlation drops significantly, up to 19%. Why? Because standard complexity formulas treat the entire frame equally, ignoring the fact that FVE aggressively compresses the periphery. To restore this correlation, we introduced a weighted complexity map. By assigning higher mathematical weights to the high-quality foveal regions, the weighted complexity map better reflects the encoded frame size. Guided by this finding, we propose FVE-CA, a complexity-aware foveated video encoding framework. Here is our system architecture. We introduce two novel middleware components, the complexity estimator and the complexity model. These modules sit perfectly between the rendering engine and the hardware encoder. They analyze the rendered frame, compute the spatial and temporal complexity, and feed a quantized complexity indicator directly into the foveation controller. This allows the system to proactively adapt to content changes, leading to more stable bitrate control. Spatial complexity reflects intra-frame spatial detail. Although more precise spatial complexity estimators exist, they incur prohibitive computational overhead for real-time VR pipelines. To satisfy ultra-low latency constraints, we use Sobel kernel as a lightweight proxy for spatial information. Temporal complexity captures inter-frame variation. While game engines provide motion vectors for geometric motion, they do not directly quantify the visual residual energy that highly correlates with encoding cost, nor are they universally accessible across different rendering pipelines. We therefore use a lightweight, universally available proxy based OTH per pixel difference between consecutive frames. However, computing pixel-level complexity for ultra-high-resolution VR frames is computationally expensive. To guarantee real-time interaction, we developed a highly optimized, GPU-accelerated compute shader using Direct3D 11. By leveraging massive GPU parallelism, where each thread group processes a specific macroblock concurrently, we achieved a negligible computational latency of just 0.9 milliseconds, adding zero perceivable delay to the streaming pipeline. So how do we turn these two maps into a single, useful number? Rather than transferring the entire pixel maps, we compress each into just two statistics values, mean and standard deviation. That gives us 4 lightweight features to work with. But raw features alone don't tell us encoding difficulty. So we collected frames from 8 VR games across 4 different genres and extracted their raw metrics with true encoded bit sizes. Using this ground truth, we trained a multivariate regression model. This model learns the nonlinear relationship between our raw extracted features and the encoder actual bit consumption behaviors, with R-squared of 0.82. The output of this model is a unified, highly accurate, and quantized complexity indicator, which we denote as the Greek letter xi. With our complexity indicator, xi, accurately predicting the frame encoded size, we can now dynamically control the foveation process. We inject this indicator directly into our QP assignment formula. As shown on the slide, the final foveated QP is determined by multiplying xi with a tunable scaling parameter, lambda. Lambda provides finer control for user on balancing visual quality and streaming stability. The logic here is simple but powerful. If a player rapidly turns their head, causing a sudden complexity spike, our indicator instantly scales up the peripheral QP before encoding begins. This proactive, mathematically driven adaptation guarantees strict adherence to target by trait. Where traditional FVE methods lack rate control, our approach fills that gap frame by frame, in real time. To validate our complexity-aware framework, we integrated FVE.ca into the open-source platform, ALVR. We evaluated across 5 distinct game genres using a Quest 3 headset. We benchmarked our approach against 2 state-of-the-art systems, complexity-agnostic CG-FVE and partially aware FOV-optics. Let's examine the results. FVE.ca significantly reduces by-trait fluctuation and cuts MTP latency by up to 37.8 milliseconds compared to CG-FVE. Perceived visual quality also achieves superior scores across both high and low complexity games. Now look at the cumulative distribution plots below. The red dashed line marks the strict target bandwidth. CG-FVE, in orange, fluctuates wildly, means severe overshoot and undershoot. FOV-optics, in blue, systematically underutilizes available bandwidth. Our method, in green, hugs the target line tightly, consistent across all 5 genres. By mathematically eliminating by-trait overshoots, we prevent network buffer bloat and ensure smooth, stable streaming. We also conducted an ablation study to understand the necessity of both spatial and temporal metrics. The figure tracks the by-trait jitter in a live streaming session. In the green area, representing moderate motion, we found that accounting for spatial complexity alone is largely sufficient to stabilize the by-trait. However, look at the red area, representing high-motion scenarios. Here, relying only on spatial complexity fails, resulting in a severe by-trait jitter of 5.22. Only when we incorporate temporal complexity, the jitter is drastically reduced to 2.67. This proves that temporal complexity awareness is indispensable for managing the unpredictability of fast-paced VR action. In conclusion, our research addresses a critical void in modern VR streaming. By bypassing the black box limitations of hardware encoders, we presented a real-time, complexity-adaptive FVE framework. Our GPU-accelerated approach accurately estimates spatio-temporal complexity in under 1 millisecond, proactively adjusting foveation parameters before encoding begins. This drastically reduces network overshoot, ensuring smoother interaction, lower latency, and higher perceptual quality across all VR environments. We will be releasing our source code to the community to drive future research in adaptive streaming. Thank you very much for your time and attention.